Labguy here. In today's video we're going to look at the sync signals for driving the Sony AVC-3400 and AVC-3450 cameras. So stay tuned. Today's video will be about operating the Sony AVC-3400 camera and the Sony AVC-3450 camera. To test these two cameras, I'm using my modified VPS5 camera adapter for operating 10-pin cameras. I modified it to accept external horizontal drive and vertical drive inputs coming from external sync generators specifically for this type of camera. I'm using the CSG-160 television sync generator, as seen in the last video, as my pulse source. I'm using the horizontal drive and the vertical drive pulses. I had to build an adapter circuit for the horizontal drive pulse on an electronics breadboard in order to develop that circuit and make it work. It works just fine. Apparently the AVC-3400 will accept the vertical drive pulse from the sync generator directly. All that was required was to terminate the pulse into a 75 ohm load so that the voltage of the pulse was less than 8 volts. It wants 7 volts peak to peak for the vertical sync. I'm feeding it 5 volts peak to peak and it's working just fine. So what does it take to operate a Sony AVC-3400 or 3450 camera? Let's look at the 10-pin connector diagram from the service manual of the AVC-3400 and find out. Looking at this diagram of the 3400's 10-pin connector, the first thing we have to provide the camera to make it operate is 12 volts DC. This is applied to pin 10 of the connector and the ground return for power is on pin 9. This powers up the camera. The next two required signals are the horizontal sync signal and vertical sync, as Sony is calling them here. These are actually the horizontal drive and the vertical drive. You'll note that the vertical sync is specified as pulses at 16.7 milliseconds, which is 60 cycles, 7 volts peak to peak with no indication of the DC level, but we know the system runs on positive 12 volts. So this signal is probably derived from a 12 volt, positive 12 volt rail and is going to be sitting somewhere between 12 volts and ground. That's all good. The pulse width is 350 microseconds and it is an active negative pulse. You'll notice that they're showing it with some roll off on the bottom of the pulse, but this is neither here nor there, not a problem. Looking at the horizontal sync or horizontal drive, it's a positive going pulse, 6 volts peak to peak, repeating at 63.5 microseconds, which is horizontal scanning frequency of 15.75 kilocycles, and it has a duration of 10 microseconds. In the case of both pulses, the front edge, the first edge, in the case of vertical, the falling edge, in the horizontal, the rising edge, those are both AC coupled through a very short time constant circuit, and so the rising edge of horizontal and the falling edge of vertical are the trigger edges that start the scanning in the camera, or more precisely, synchronize the scanning in the camera. You'll note that the vertical is an active low signal and the horizontal is an active high signal. The sync generator puts out both of these pulses as active low signals. So we need to buffer the horizontal sync pulse and invert it. Looking at the next diagram, you'll see on the top of the page my simple circuit for performing this pulse reception and inversion. The pulse from the sync generator, any one of them, can come in the input and is terminated into a 75 ohm resistor. With correct termination, the pulse is a DC referenced pulse referenced at 0 volts and pulsing to -4 volts. To get rid of this DC component, I AC couple the pulse across a 4.7 microfarad non-polarized capacitor into the base of a 2N3904 transistor wired as a simple inverting circuit. The 5.6K resistor provides approximately 700 microamps of pull-up current to the base of the transistor to turn it on, so that in the absence of any drive, the output of the transistor, the collector, will be at ground potential. It will pull down. The 1K resistor limits the current to 5 milliamps. This circuit is being operated at 5 volts, and apparently a 5 volt pulse is adequate to synchronize the horizontal scan in the Sony AVC-3400 and 3450 cameras. Looking at the upper trace is the vertical drive, and it is being fed into the camera's vertical drive input. And it works just fine at 4 volts peak to peak. The camera says it wants 7 volts peak to peak, but I believe this is simply the level that the VTR generated that sent the signal up there. The input is the base of a transistor very similar to my circuit. In fact, my circuit's derived from their camera circuit. It operates just fine on the 4 volt peak to peak vertical drive pulse. The bottom trace shows the inverted horizontal drive signal required by the camera and specified as 6 volts peak to peak. My circuit is providing this pulse at 5 volts peak to peak. Otherwise, the numbers given, 63.5 microseconds and 10 microsecond requirements, are being met. Let's begin by doing a quick overview of the AVC-3400 camera and its operation and features. You have the primary camera body containing a vidicon tube television camera and a tiny cathode ray tube video monitor. It has a microphone built in on the front and is intended to be used with a portable video tape recorder. It's equipped with a 6:1 zoom lens with a range of 12.5 to 75 millimeters. It has an f-stop of f1.8. This is the f-stop ring, or the iris control on the lens, which controls the amount of light that enters the camera. And a unique feature that will reveal if you have a television camera lens is it has a closed position. This is to protect the vidicon tube from inadvertently being pointed at the sun or at other high intensity light sources. It also has a lens cap as a backup for the same reason. There is a zoom ring, which is the middle ring, and then the outer barrel of the lens is the focus control, optical focus that is. On the back side, The camera has a magnifying lens that can be flipped up. This magnifying lens is for viewing the built-in 1-inch television monitor, which you may or may not be able to see. This camera is currently not powered on, obviously. The camera has no electronic adjustments on the outside. All electronic adjustments are internal, and we will look at those in a moment. The 3450 also has a removable pistol grip handle, which contains the trigger switch for starting and stopping the tape recorder. On the tripod mounted camera, the trigger switch is a mechanical button on the other side, right here, and can be operated when the pistol grip is not installed. And the pistol grip is equipped with 2 legs that fold down so that the camera can be parked on a tabletop for viewing of the viewfinder this way. Yes, I have several of these cameras. At this time, I am going to show you the proper way to open this camera so that you don't damage your camera if you have one of these. So follow this procedure as I illustrate it here. The first thing you do is remove the pistol grip. You flip the camera upside down. I didn't mention it, but it has 4 little feet on the top side so that the camera can be parked like this. Turn the thumb screw underneath these legs to loosen the pistol grip and remove it. Put it aside, don't lose it. It's probably easier to do this with the lens off, but I'm going to do it with the lens on. So the next step is to remove the 4 top cover screws. There are 2 on each side. And don't lose them. All screws in this camera are metric. All right. The camera cable is permanently attached, so get used to the notion that it will always be in your way. So now we've loosened the cover and it comes off. Don't lose it. This is one side of the camera. This is the other. You can see the 1-inch viewfinder right here. This camera was designed in 1969, and the CRT is very unique in that it is magnetic focus, and this ring right here is a donut magnet. Do not lose this magnet. You can't focus the CRT without it. Clearly, somebody thought this was camera 1. Oh, I see I didn't cover up the property tag. I didn't steal it, honest. Okay, we have the top cover off, and you'll see there are some pots along the top edge of the board. 1, 2, 3, 4, 5, and 6. Don't turn these. We're going to cover what they adjust in a moment, but first we have to get to the other adjustments. One of the others is right here on the side. This metal box is the video amplifier. This down here, this metal cylinder, is the deflection yoke housing the vidicon tube. Notice that the lens is placed to focus the image onto the face of the tube. Now, to get to the camera controls, these are viewfinder controls mostly. To get to the camera controls, we have to remove this bottom cover plate. It is held on by 2 screws. And they are small Phillips head screws. And 1, 2, and needless to say, don't lose them. They are tiny. And this cover comes off with some effort. There we go. And it has an opening large enough to get the 10-pin connector through. Now put this aside and don't lose it. Oh. What the heck? I've been inside this camera before. It's true, I have. I labeled all the controls. So on the bottom, I really don't want to hold it that way. On the bottom, let me get this cable out of the way. There we go. All the camera controls are towards the back, the viewfinder end. And they are the vidicon beam control, the vidicon electronic focus control, vidicon vertical linearity, vidicon vertical height control, scan vertical centering and horizontal centering of the image in the vidicon tube. Don't turn these. The 2 that you would adjust normally, if your camera has a weak tube, is you will adjust the beam and the focus controls. You can do this with the camera mounted to a tripod. But watch out. Right here is the high voltage power supply. It has a fish paper cover. It can be removed. And I recommend that you don't, because you'll be exposed to the high voltages that run the CRT, which runs on 3 kilovolts, and the vidicon voltages, which are as high as 400 volts. So just leave that paper cover on. There is nothing user serviceable underneath this cover. This control is the target control. That is the target voltage on the vidicon. The target is the photosensitive surface, and this voltage is part of a automatic level control, or ALC. So when you adjust it, you have to move it a little and wait. You have to set the camera up pointed at a test subject that is lit correctly, and then adjust this carefully. Alright. Here are the controls on the top of the camera, starting back here. This is the 9-volt DC adjust. If the paint dot is not broken on this control, don't adjust it. It's probably okay. The next control here is viewfinder contrast. This sets the contrast of this CRT. The next control is viewfinder brightness. It sets the brightness of the viewfinder CRT. The next control is viewfinder bias. This adjusts one of the grids in the CRT, and it's probably best not to adjust this one. The next one is viewfinder height. If the paint dot is not broken, don't touch it unless you have to adjust the viewfinder height. But the chances are, if your viewfinder has a shrunken image or its linearity in vertical is out of whack, you probably need to replace the electrolytic capacitors on this board. The last control is viewfinder vertical linearity control. Linearity is to make the scan straight so that the height of an object in the upper half of a scan is the same size as in the lower. Again, don't adjust it unless it's clearly distorted. You set linearity by pointing the camera at a circle, a perfect circle, and then adjusting these controls to make that circle look round on the television. So this is the moment the viewers have been waiting for. We're going to turn this camera on and demonstrate it in operation. I asked a couple of my cohorts to come in and model for us today, and so let's see how this works. And I'm going to demonstrate to you the cold start of a vidicon camera because I find it fascinating the way they start up. So right now the camera is off and aimed at our subject, so I'm going to get in the picture to turn on the switch, and then we'll give it however many seconds it takes for the vidicon tube to warm up and for the picture to appear. I never get tired of that. I call it wiping in. So there's Spud and Felix, and they're hamming it up for us, and that is what the image quality is of a direct optimized scene. So now I'm going to go over and operate the 3400 for you, and you'll see classic vidicon video. Here we go. There's a shot of my computer screen and the very camera that is shooting this video. I'll look around the room a little bit, and you'll see that there isn't much light out there, even though the room is well lit. My desktop is pretty well lit. My coffee cup and other desktop detritus. You note that if we wait a few seconds, the picture improves slightly, and that is the automatic level control at work. But when there's a bright object in the scene, like now, the dark areas get darker. But if we get the bright stuff out, we can see darker objects. So, back to my cohorts and a couple of my recent projects, like the 10-4 Eleanor. This is full zoom here. Spud and Felix. The NBTV cathode ray televisor with the little itty bitty speaker I added since the last time you folks saw that. And so that is pretty much the operation of the AVC-3400. I have photo floodlights on right now. It's supposed to be the equivalent of 600 watts of incandescent light, but I have my doubts. So that's off the preview monitor. let's take a look at the viewfinder in the back of the AVC-3400 camera. Alright, we are currently not white balanced, and I'm not going to white balance for this shot because I've white balanced the camera for the P4 phosphor in the CRT. So there's Spud and Felix, and we come over behind the camera and we come around and we look into the viewfinder as well as we can. It looks washed out, but it is not. So that is what the camera operator would see when operating the camera. And there is the magnifier for the eyeball. And so that is the operation of the AVC-3400 by Sony. This camera came out on the market in 1969 with the companion AV-3400 reel-to-reel black and white videotape recorder. Sorry, I'm in the light. We wing these things here at Labguy's World. Labguy likes what's inside the cameras and was never very good at what you do outside the camera. So let's move on and look at some waveforms, shall we? These are the three primary waveforms of the Sony AVC-3400. We are looking at the video on my digital oscilloscope at vertical rate. This pulse and this pulse are vertical drive. Every time this pulses, the camera will start a new scan from the top moving down. So from here to here is 1/60th of a second, and that's one field of video. The waveform at the top is the video output of the camera, and you can see me kind of moving around in it. And I'll get out of the way, and that is what the waveform at vertical rate on a digital sampling oscilloscope looks like when video is displayed at this speed. So now let's open up the scanning on the oscilloscope so that we can see the horizontal drive. From here to here there are 262.5 pulses, but due to the nature of a sampling oscilloscope they are blurred together into a band. Back up. All right. I've opened it up so that we're looking at one vertical drive pulse, and you'll note that I told you that the falling edge of the pulse starts the camera scanning. That resets the vertical scan in the camera, and for this duration the image is blanked off while the beam goes from the bottom of the tube back to the top. It's actually upside down because the lens inverts the image. But we'll just assume everything's right side up for this discussion. So during this short time they turn off the video, and including the sync. Well, this is the substitute for a proper sync pulse. Then down here, each one of these pulses is one scan line of video. So let me change the trigger on the oscilloscope to look at that channel. instead, and we can open it up so that we can see individual lines of video. Now we're looking at a period of time that is one line wide. The reason it's bumping up and down is because the oscilloscope is scanning once for every 2 TV lines. And so it's working its way through all of the TV lines, and when you see it bump down to here, you'll see that bump there. That's the vertical sync pulse passing through. So, looking at the video on the scope, let's see, I have something bright. There we go. Well, it's hard to see. It's hard to demonstrate it because the ruler is actually quite blurry at that distance. I'm trying to insert the ruler in there so you can see it, but it's not working. It works better with this analog oscilloscope. So, what we're looking at, horizontal drive. Let me get my pointer. How unprofessional. Horizontal drive and video with the sync pulse here. Blanking, which is really crappy, probably bad capacitors. This little jagged lump here should be a flat horizontal line. That is the horizontal back porch. There's virtually no front porch. So clearly this camera either produces a very poor signal or it needs components replaced. Probably the latter. And this section constitutes the live video that we see on the screen. So, thanks to us putting in sync pulses from the sync generator, our scanning in the camera is in time with our sync generator there, and it's in time with the sync generator there at vertical speed. This is vertical scanning speed. This is the interval of time when the electron beam is going from the bottom of the screen back to the top, and then it's blanked off for some number of lines until we reach active video again right here. So in real television, this interval is 21.5 lines of blanking. I'm not going to count those because I'm pretty sure this camera doesn't use counting methods to generate the blanking time. Probably uses a capacitor charging system, which can vary plus or minus 1 or 2 lines, which is no problem for just if you're going to just look at this on a black and white television. So those are the video and sync waveforms of the Sony AVC-3400 camera in operation. We're not going to look at the AVC-3450 in this video because operationally it's identical. Internally it's exactly the same as the 3400, only completely different. So it's got all the same adjustments. They're in a different place, and otherwise the two cameras are extremely comparable to each other. The difference being 5 years of time. The 3450 weighs 4 pounds. The 3400 weighs 7 pounds. That is the primary difference, was to come out with a lighter and probably cheaper camera for the outfit just about the time that the entire reel-to-reel systems became obsolete with the arrival of Betamax and VHS. My favorite time in history is everything before Betamax and VHS. Holy cow! I didn't see you there. I was shooting the video you've just been watching. I hope you folks enjoyed this. This dive into the old Sony cameras. I hope you enjoy them as much as I do. I hope you found the video informative, and I hope you got something out of all of that. That's the Sony AVC-3400 and AVC-3450 cameras and how they operate. I'd like to welcome all of the new subscribers. They're just signing up like mad now. And as usual, I send a wonderful greeting to all of my current subscribers. Thank you. Thank you very much for watching my videos. I appreciate it. It keeps me driven to make more videos for you, and my attempt to produce subject matter that nobody else on YouTube covers. I challenge you to find anyone who deep dives into old video gear like I do. So, again, thank you for watching. You know all the cliches. You know what to do. And leave your comments. Do the other things. And until next time, Labguy out.